Hi, welcome back. Today what we're going to do is we're going to get into a little deeper into the laser and talk about laser pump chambers. And effectively I'm going to describe both some of the design considerations and also how to fabricate them. And we'll start out with the basic concept. In this laser, as I've described previously, I've already have a mounted medium, a dye cell, and a mounted flash lamp. So the only purpose of the reflector that you're going to put around these is to transfer the light from the lamp to the medium. Now this applies both to flash lamps as well as arc lamps for, say, YAG lasers, and even for non-focused diffuse laser diodes that are used to pump with the IR. But essentially what you need to do is you need to move the light from a diffuse source such as a flash lamp and get as much of it as possible into the dye cell. Now, one way to sort of imagine that you would do this is if you took a cylindrical tube with a highly reflective mirror-like surface on the inside and placed the flash lamp on the inside of that tube at the very center. Light given off by that flash lamp would impinge on the surface of the tube and would be focused right back to that same point. The lamp is at its own focus. However, if you take that cylinder and you compress it along one axis, you form an ellipse. And an ellipse has two foci. And depending on the ratio of the minor to the major axis of your ellipse, you can determine how far apart those two focuses or foci in that elliptical cylinder is. You can use basic high school geometry to make that determination. But if you already have an assembled lamp and an assembled cell, you know what the distances are that you need in order to have those foci correspond to the two tubes. And so by doing simple calculations, you can fabricate or you can design a reflective elliptical cylinder that runs along the length and transfers the light from one to the other. The consideration there, though, is that any kind of an imaging reflector like that has to have a metallic coating on the inside. And the best metallic coatings, if you're in the IR, would be, say, copper or gold. If you're in the UV or visible, it would be aluminum. And the best that you're going to get out of them is about 91% reflectivity per pass. And because an elliptical cylinder requires two bounces of the light from the lamp to the inside of the cylinder to the other half of the cylinder and down to the cell, you effectively have a reflective transmission or transfer of about 82%. You also, though, have to have a perfectly shaped ellipse, and you have to have the ellipse perfectly aligned in all three axes. It has to be aligned rotationally, it has to be aligned in the vertical and in the horizontal plane. So it's consideration when you mount such a cylinder. In addition, one of the limitations of any kind of an imaging reflector is that you can't image a diffuse source smaller than the size of the source. So in other words, the most efficient coupling is going to occur when you have the flash lamp no larger than the diameter of the dye cell, and that is a significant limitation. Because the practical aspects of alignment and the moderate reflectivity and the fact that you can't focus the light any tighter than the lamp means that I didn't go after the imaging reflector. Most lasers, I believe nowadays, and certainly this laser works better, with a non-imaging reflector. And what that does is instead of having a mirror surface on the inside, you have a surface, I don't know if you're able to see inside here, but as I took away one half of this reflector, the inside looks white. And that's because the reflective material that I have on there is a diffuse coating out of barium sulfate. And any of the diffuse coatings, whether it's magnesium oxide, alumina on ceramic tubes, or even polytetrafluoroethylene, which is Teflon, they have enormously higher reflectivities than the mirror-like materials like aluminum and copper and gold. So even though the reflection inside is not limited to just 2 bounces, it may take 5 or 6 bounces for the light to get from the lamp to the medium, it's still a more efficient means of coupling. In addition, because of the fact that the tube doesn't have any alignment requirements, you don't even have to have a shape like an ellipse. For two tubes next to each other, an ellipse isn't a bad shape, but it could be square if it's easier to fabricate it square. It's just basically got to surround the tubes, which really makes installation a lot easier. In addition to that, the fact that the ratio of the efficiency in the coupling is related to the reflectivity of your coating and the relative size of your cell to the inner surface area of your cylinder. The tighter, smaller your cylinder is, the more efficient the coupling. So that's why another name for this type of reflector or system is a close coupled system, because you want it as small as possible. And if you make it really small, very tight, and it's very highly reflective, you can actually couple the light from the lamp to a diameter smaller than the lamp is. There's a whole bunch of reasons why that's an advantage, because you get more intensity in your medium. You can use larger lamps which have higher explosion energies, and also because they're larger in diameter, are faster. So that's why I decided to go ahead with the non-imaging reflector, and the fabrication of the reflector requires a couple of considerations. But basically you have to consider that you want to be able to bend it, at the same time you want it to have some stiffness. And what I found is that the material that I get from a company in Canada called Animet is a 0.02 inch or 20 thousandths inch thick aluminum sheet that has a dielectric stack or an enhanced coating over the surface to protect the aluminum from abrasion as well as oxidation. And the advantage of having the enhanced aluminum as opposed to, say, just an overcoated aluminum is because some of the coatings, especially the barium sulfate, can corrode the aluminum that's underneath it and darken it and decrease the effective reflectivity. The multi-layer dielectrics that are used to make the enhanced aluminum, those reflective coatings actually provide more protection for the overlying paint white coating that you're going to put on top. The enhancement doesn't really make the reflector in the imaging scenario any better, because the enhancement is somewhat bandwidth limited and it's also angle of incidence limited, so it's not really an advantage over just the aluminum. It's not a way to cheat the original system. So the way that you would then design the system is you determine, first of all, how long it's going to be. The longer your tube, actually the more efficient the coupling, because you have less light loss at the ends. That's one of the arguments for making it long. But you determine the length based on the fact that you want it as long as you can get it, but not so long that it's going to be at risk of shorting out your electrical system. So that's a consideration. But once you've determined the length, then you need to determine how much material you need to go around. Now that's fairly simple. You can take a string, you could take a flexible tape, or what you could do is you could take a piece of the material that you've used, cut a strip and bend it around. Once you've determined what that distance is, add about 2 centimeters or an inch to that total, because you're going to overlap these two halves, and then divide the number in half. What I then do is I go to a professional or a local machine shop, and I have it professionally slit, so I get a very nice square, burr-free, square, rectangular piece of material to do the bending. And so what I'll show you next is how I fabricate the shape out of that material. Okay, now what I'm going to do is I'm going to take one of these pieces of aluminum and mark a center line in the middle between the two sides and right down the middle of this sheet, identifying the center line and also giving me a position that I'm going to use to drill 3 tiny little holes that I will then place on this bending jig that I fabricated. The bending jig is a piece of, I'll use English measure here, 3/4 inch PVC tubing on a 3/4 inch board. Well, the standards are a little bit different. But basically what it does is, by placing a groove in the end, routing the groove in the middle of the wood, right down its center, and then putting a little dollop of epoxy in there and putting this PVC pipe down on top and some packing tape to hold it down overnight, I get a very rigid, round, soft material that then has a slight overhang to the lower part, so that when I end up bending the sheet of material on here, that overhang allows me to get a little bit of spring back and end up with a nice U-shaped bend. The 3 holes that I placed in this sheet are then transferred to the pipe. I then take this off, drill and tap that, and actually mount this with 3 small screws. This provides a very centered aluminum support for the aluminum doesn't allow it to get out of alignment when I do the bending. And then literally, I bend it by hand. It turns out that I've tried to use a press and I've tried mechanical means. I get just the same result. It's far faster. And effectively what you do is you just press down on the material with your hands and you kind of work yourself along the material, and as you do, it'll start to bend. I'll give you a little bit of an example. It starts to take a little bit of a bend, and then as you continue to do it, you get a little bit more of a bend, and over time, you end up with a material that remains very smooth. There's no wobble in the material. This was done the exact same way on this jig, and as you can see, there's no sort of wobble in the alignment here. You can visualize this when you're doing it. You can sort of see if you need to press a little bit. But it is very easy to do. There's no learning curve to this. 5 minutes and you have an excellent curvature in this material. You bend both of the pieces that you're going to make. You've essentially fabricated 2 of these identical reflectors. Then you take one of the reflectors and you cut a little notch in there for the cooling tubes that would be on the lamp side. And then you take the 2 reflectors and literally mount them on the laser. What happens is one of the tubes, if you tend to be really compulsive about it, if you overbend it a little bit so that it's a little smaller than, say, the U shape of a perfectly parallel sidewall, that material can then capture the other one and give you a nice tight fit on the overlap. And when you put these 2 halves together on the laser, you'll get an overlap of about, let's say about a centimeter or half an inch. You then draw a line along that material, along that overlap, so you can tell how far one nested inside the other one. You then take the 2 tubes apart, and on one of them, you transfer that distance to the inside, and you place some painter's tape carefully along that point. And it's important to be pretty straight here. And so it might take you a couple of passes, but effectively you want a nice straight line on both inner surfaces of one of these reflectors. What you'll then do is you'll simply paint it. And the painting process is just like doing any kind of a spray painter. And I'll step over to this other table here and I'll show you how I do that. So now that I've had the two reflectors bent, what I then do is I paint it. And the way that I paint this is you need to use a special kind of paint. What I should start with is the barium sulfate is usually provided as a concentrate. You can get it from optical supply shops. It's basically the Kodak 6080 reflective paint that is an emulsion of barium sulfate and a couple of other inorganic ions. And what you do is you dilute this material, and I've found that the best dilution is about a 50% isopropyl alcohol distilled water. So 50-50 isopropyl distilled water. And that total volume of solvent is then mixed to an equal volume of the concentrate. So if you get a liter of concentrate, you end up with 2 liters of paint. And that mixture gives you about the best drying time as well as the thinnest, easiest to paint kind of viscosity. The material doesn't paint well with an airbrush. I tried that. It's too thick. It's kind of like sort of a light, heavy cream. But a high volume, low pressure spray painter like Fuji manufacturers, for example, does a very good job. The interesting thing about this kind of painting, though, is that the material dries extremely quickly. And so when you place this up against some sort of a backdrop and you begin the painting process, you'll put on 1-2 passes, done. And then you wait about 3 or 4 minutes, rotate the part, and do it again. You have to put on about 15 or 16 coats, but they come pretty quickly, so it takes you about an hour to get the coating on. Once you're done, though, it produces a very nice surface. This is the actual reflector from the laser. I took this off. And as you can see, it's really nice. The only places you can see a few little defects are in the metal here where I had gotten some static electricity shots or discharges when some of the flash lamps were not charging properly. But nevertheless, you can see that the white is perfect. And if you do get dirt or you do get defects, it's easy to touch this up with just a couple more coats of the reflector material. As a consequence of the taping process, you can see that you have that little clear gap. And so that when you nest the 2 cylinders together, the one that has no coating on it is the one that goes on the outside. The other one is fully coated with reflective material, and so as a result it doesn't get scratched by sort of trying to scrape the metal into the reflective material. The material also does not absorb light, so even if some dust or some particles or some debris drops off of this because of abrasion, it doesn't burn on the tubes because it is reflective, so it isn't a real problem. And as long as you mount this where you're not doing a lot of very physical activity that would touch the coating, it remains good for a very long time. The other consideration with the pump chamber is that the cell itself, here's an example of one of the early versions of this dye laser when I had a larger diameter cell. And the cell is fabricated out of quartz for good UV transmission. I have it enlarged at the ends just to make it easier to mount. But you'll notice that the surface of the material in the middle is matte. It looks like a ground glass, and it is ground. The reason for that is in any kind of a dense material, whether it's a rod or whether it's a liquid, there is a potential for spurious types of laser ray paths that can pass through the tube that can actually bounce within the tube, glance along the surface between the liquid and the glass, or in a solid rod, between the glass or the crystal and the outer air. And that can produce a lot of halo light coming out of the end of the laser. It can also deplete some of the excited state molecules that are needed to run the laser operation along the path you intend by depleting them by these spurious pathways. They're called whispering modes or amplified spontaneous emission, but to prevent that from happening, by making the surface of a rod rough or the inner surface of the tube rough, when a glancing ray hits it, it diffuses quickly and doesn't have enough time to build up enough energy to do that damage to the beam. When you're dealing with larger diameter tubes, it's relatively easy to mechanically abrade it. I use a brush that I dab in some dish soap and some abrasive material, and literally do sort of a bottle brush cleaning operation. Just push it in, push it out. You can even mount it, as I did at one point, on a drill and sort of pass the drill in and out of the tube. And within 10 minutes or so, you have a very nice matte finish. The problem is, as the tubes become smaller and smaller and longer, you just can't do this mechanically without damaging something. At that point, you've got two options. One is you can use chemical etching. And as an example, I used hydrofluoric acid. This is concentrated hydrofluoric acid, and for all you fun monitors out there, yes, this is extremely hazardous. And as I explained in the previous video, when we go into different areas of technology beside lasers, we're going to talk about chemistry. We'll talk about some of the means that you can use to mitigate some of the hazards with some of the materials we use. But nevertheless, the chemical etching does work very well. If you do it safely, it does provide a matte surface. But it provides a surface that's not very coarse, and it's not that diffusing. And so I found that I got a better result by using, again, mechanical means, but I did it in a little different way. What I did is I took a commercial sandblaster, first time use, so it wasn't dirty, and it's gravity fed, and I fill it with 120 grit silicon carbide abrasive material. And then I take the normal nozzle that goes on the front of this, and I modified it by placing this alumina or ceramic rod in the nozzle, so that when I place this in here, I have sort of a long gun with a long tip. And this alumina stands up to the abrasive material pretty well. You can then place this into even a tiny diameter tube. I mount them on a couple ring stands. I take a vacuum filter bag from a shop vac, tape it on the far end of the tube, and then I place this rod into the tube like this, insert it into the tube, and then begin blasting and drawing it out. And after a couple of random rotations, I then turn the whole thing around, because the tube is obviously longer than a convenient rod is, and so as a result, I blast it from both ends. End result, I use about a pound of abrasive. It's extremely clean. The only mess that I make from this is the process of just filling the sandblaster. And you end up with a nice coarse finish, and you can even reuse the material from the bag. You can put it right back in the container because it's essentially clean except for a little bit of the silicon oxide from the tube. That matte finish then provides a very good reflective diffuser, much better than the hydrofluoric acid used, and obviously you don't have to get hydrofluoric acid. Final little caveat is that these tubes, even if they're fabricated by very good glass blowers, still can sometimes have a little bit of a bow to them. And when you're trying to pass light down a tube and it's got a bend to it, obviously there's going to be some occlusion of the light path. What I do is I take this tube, it doesn't have to have the flanged ends, but that makes it a little bit easier, and I roll it on a flat surface and determine where the bow is in the downward direction. I then mark the sides of the tube, and if you go back to the video earlier on, you'll see that there's a couple of black lines on the side of my die cell that's actually installed in the laser. And therefore I know that when I mount the tube, its bow is in the perfectly downward direction. It's then easy to place a small support underneath here to elevate it maybe 0.5 millimeter or whatever is necessary to make it absolutely straight along its length. So by using these techniques, I've gotten a very convenient method of getting very high efficiency out of the laser. And as a result, I think even though I'm limited by my optics at this point just because of damage, the potential of this laser to produce much more energy than I demonstrated before is there, and I think the cavity optics are a big part of it. So I think we'll probably finish up this series of videos about this particular laser in a little bit, and that's where I'll get into the deep water on the optical cavity itself. What's the mirror and lens and the optical process that's going on within the laser that allows it to produce the beams that it does. So I appreciate you watching tonight. I hope you enjoyed it. Good night.